In the last part of the lesson, we looked at a single simple current mirror, and it's useful to note that we can actually extend a single bias generation or a single VB generator across to multiple current sources. And the way we would do so is something like the following. So we start with our simple VB generator. We have some reference current going through our resistance. We'll call the reference current IR. We have our diode connected transistor. And it has some dimension W over L1. Now we might have a couple of different circuits that we'd like to generate bias voltages for. For instance, we might have a differential amplifier. We'll look at differential amplifiers a little bit later in the course. But we bias differential amplifiers with current sources. So here's an Nmos current source. So we'd send this VB over to the gate of that current source, and of course some current would flow through it. Now, of course, we might make M2 equal to 2 times W over L1, in which case twice the current would flow through this branch as is flowing in the reference branch. And of course we could have an amplifier, another amplifier, maybe a cascode amplifier. We'll look at cascode amplifiers in more detail shortly. And we're biasing this cascode with a current source. We're going to tie it to that same VB node. And maybe we make M3 here equal to 4 times W over L1, in which case the current flowing through this branch, I3, would equal 4 times IR. Now the reason that we might do something like this is that it costs us current in order to generate this bias voltage, and of course we know that power is equal to voltage times current. So in this case our power is coming from VDD. We have a reference current IR. So we have a power cost in order to generate this bias voltage. So we'd like to use it as many times as possible throughout the circuit in order to maximize the reuse of the voltage and the efficiency of the circuit. In other words, less power wasted generating bias voltages, more power wasted generating currents that are being used for amplification. Now we can also make current mirrors out of bipolar transistors, and of course in the lab last week you've already done so. So here's our bipolar current mirror. We have a diode connected BJT, and we send it the the base voltage to an identical BJT, or perhaps a scaled version of this BJT, Q2, and of course our reference current here flows through Q2, generates a bias voltage VB, which causes a current I2 to flow through transistor Q2. Now we can solve this circuit by doing a KCL at this supernode. And when we do KCL at the supernode, we would note that IR is equal to IC1, the collector current in transistor 1, plus IB1, the base current flowing into transistor Q1, plus IB2, which is the base current flowing into transistor Q2. And of course, we can use our beta relationship and say that this is equal to IC1 plus IC1 divided by beta plus IC2 divided by beta. And we can make a further assumption that our IC1 is approximately equal to IC2 in the case where we're trying to make IR equal to I2 here. And we can further write IR is equal to IC1 times 1 plus 2 divided by beta. Or we can say that IC1 is equal to IC2 is equal to IR divided by 1 plus 2 divided by beta. Now what's interesting here is that this is a systematic error term. Remember, we wanted IC1 equal to IC2 equal to the reference current, but here we're saying that IC1 is, IC2 is equal to the reference current divided by 1 plus 2 over beta. So if beta is very, very large, then IC2 is equal to the reference current. But in cases where beta is not very large, we get this systematic error. We note that this doesn't happen in MOS transistors because in MOS transistors, what causes the error in the bipolar transistor is the base current. MOS transistors don't have any gate current flowing ideally, and so they don't have this systematic error term. In the next part of the lesson, we're going to learn how to deal with a systematic error in bipolar transistors by reducing the amount of base current that flows into the transistor.